So this is the problem solving session for course Basic Electronics, coded as NOC 23E62. This is week 9 for April 1st, 2023, and my name is Abid Bansal. I am a PhD scholar at IISc Bengaluru. Over the past 8 sessions, we have been talking about, as the topic suggests, about electronics, some relevant topics of electronics. The first session we talked about Thevenin and Norton equivalence and the nodal analysis of the circuits and the superposition theorem. Finally, we had looked at the phasors. Phasors are nothing but the sinusoidally steady state of various currents and voltages that we frequently encounter in our problems related to the for circuits of basic electronics. And then we saw some transients, primarily RC transients and some RL transients, and we saw that how the switching impact, how does a waveform of different nodes, voltages and currents change as we switch from one position to other. Then we switched on to circuits, so various diode based circuits in session 3 like clamper, B detector and so on. And then continuing with the diode based circuits, we saw one more in session 4, that is half wave rectifier. And finally we jumped to BJT circuits, primarily the biasing of the DC biasing of the BJT circuits. Recall the BJT has three components, three terminals primarily, emitter, base and collector, and how you can bias them in different different ways to get different characteristics out of a BJT. Then we saw one of the most commonly used biasing schemes, which is used to implement common emitter amplifier. And then we saw the AC analysis of BJTs using the hybrid pi model and T model. And finally an application of the BJT based circuits in the form of push-pull amplifier. For session 6, we talked about ideal op-amp circuits. I'll again briefly visit what do we mean by ideal. And then in session 7, we talked about non-ideal op-amp circuits and difference amplifier. In session 8, that was the last session, we had talked about much more advanced circuits of op-amp in the name of precision amplifier. And then we saw the frequency response of an op-amp and how we can use it as a filter. And in that in that discussion, we had talked about the transfer functions and the Bode plots, and how do we interpret, how do we, let's say for a given transfer function, how do you plot the Bode plots for magnitude as well as phase, and vice versa. That is, you are given magnitude Bode plot and phase Bode plot, then how do you obtain the transfer function. So we saw that. So in today's class, again, first I'll briefly visit what an operational amplifier is. So as the name suggests, it performs some operations. Some of the very basic operations are comparison, integration, addition, subtraction, differentiation. And it's an amplifier. It's one of the most common applications that are of an amplifier. That is, you provide it some input voltage. So let's say I'm providing it some input voltage, very small, right, and it will transform it to a large value. So it has amplified. So peak to peak, you can see it has amplified it manifold. So that's what I mean by that it amplifies input voltage. And the key thing, topologically, or how does it look like what components are there, so you can treat it as a subclass of differential amplifier. So this is on the left of your screens, you can see a differential amplifier, which is been made out of some BJTs and some resistors, and VCC and VE are your power supplies. So in this configuration, where I'm providing two inputs, V in plus and V in minus, and I'm taking output in such a fashion as is visible on your screen, the output voltage can be written in this form, where AD is often referred to as the differential gain, and AC is referred to as the common mode gain. So no, I'll repeat that this is a differential amplifier that is on your screens, this circuit on the left. If we design it in such a manner that AD is much larger than AC, note AD is differential gain and AC is common mode gain, and we again design in such a manner that this complete circuit has a high input impedance and low output impedance, this differential amplifier can be treated as an operational amplifier, which is denoted by this symbol. So you can see V plus and V minus, these are the inputs that you see over here. Vs plus is nothing but VCC, Vs minus is nothing but VEE, and V out is the same that you see over here. So this circuit, again, this is a very simplistic picture. There are many more components, but this can be converted to an operational amplifier. Okay, and these are the conditions that are required. Put it in a different format. So this is again differential. Yeah.
Sure. Just one question.
Yeah.
In differential amplifier, how do you get common mode gain?
So the way to get common mode gain is, I'll just explain it mathematically, so that
differential mode means differential gain will be there, no?
No. See, the name is differential amplifier, right? But it doesn't mean that it always give a differential gain. For instance, if let's say you provide V in plus as plus 1 volts and V in minus
Hmm.
also as plus 1 volts. So what happens is
Okay.
that this term will vanish, the first term you're seeing, right? V in
Hmm.
plus minus. So this term will vanish. So output voltage will be dependent on common mode gain, and this will 1 plus 1 divided by 2. So this will also come out to be 1. Correct? So whatever output
Hmm.
voltage you are getting will be mathematically, the number will be equal to whatever the value of AC is. Okay, so that's how we obtain common mode gain. Usually what happens is that this we design it in such a manner that we want to operate in a differential mode. Okay, but this is something you can call it a side effect. But there are circuits where there may be an application where you want to operate in common mode. Okay,
So in Wien plus and Wien minus both are different voltages.
these are, yes, that's why I'm denoting in different manner. These are completely independent of each other. Okay, they have no relation
Okay.
to each other. These are independent. So the
Okay.
way I can say it is that V out is a function of V in plus and V in minus. These two are independent variables. Okay, and this is the dependent variable. Are we good?
Yes, sir. Yes.
Okay, all right. So as I was saying, this is the differential amplifier, and this is, you can see, this is a very crude model of an operational amplifier. This is a very crude model of an operational amplifier. You can see V plus and V minus. These are the inputs. Vs plus Vs minus are the saturation voltages, and this is the output that I am taking. Now, there are various parameters that we associate with an operational amplifier. The most common ones are listed here. One is the open loop gain, denoted by G or AOL. Its ideal value is infinity, but in the market which you will find it 10 to the power 5, 10 to the power 4, somewhat of that range. Output voltage, which is denoted by V out, you can see over here, is infinity for an ideal op amp. Is not, is it saturates a VSAT. So this is the VSAT that I'm talking about. It can be, let's say, plus 15 volts and minus 15 volts, right? So the output voltage cannot go higher than these voltages from the upside, and this is from the on the negative side. So the input impedance, I told you that input impedance has to be infinity, right? But that's not the case. Real values in some mega ohms, which is good enough. Similarly, output impedance, which you can see over here, by the way, this is the Rn that I was talking about. R out, ideal value is 0. Real value is a few ohms, or if it's a very good design, maybe a few milliohms. Offset voltage, we saw when we talked about non-idealities in the op-amp circuits. If you have for more details, you can visit that video, which is on my YouTube channel. But offset voltage is something that typically what we want, which I just talked about, that here, if V in plus is equal to V in minus, right? And both of them, or if both of these are 0, everything, you are not providing any input, you should ideally get an output voltage of 0. That is not the case, because really there is some mismatch between BJTs or some resistances, and there are many non-idealities. So just to counter that, we provide some offset voltage. As I told you, more details are in the lectures of Professor Patil, and if you want to see some problems, you can visit the YouTube channel. Similarly, this is an important term, CMRR, common mode reaction ratio. It is defined as 20 log AD upon AC, right? As I told you, AD must be very large than AC, then only we call it a good operational amplifier, right? So if AD is 3 orders higher, then this value will come out to be 60. If AD is 5 times higher, this means differential gain is much 5 times 5 orders magnitude larger, then it will be 100 dB. Higher the value of CMRR, so ideally it can be infinity, but for practical devices, we find in the range of 60 to 100 dB, which serves our purpose. So usually, so what we do is that this will never be true, right? But we operate with these values, some real values. Okay, so this is the, just for the sake of comparison, I have drawn this table. All right, and this is just a summary. This is, again, I have drawn it a different format. You can see the two inputs, V plus and V minus. This plus input is also known as non-inverting input, because whatever input is provided, the output is in phase. So we saw in previous 2-3 classes, that was the case always. Similarly, if you provide an input to this terminal, right, output voltage will be out of phase with input voltage. You can see also with this formula, right? So that's there are some these are some nomenclatures. It's good to just keep it in mind. And again, this plus V is nothing but plus V sat. So there are different ways in which people write it. So this is nothing but the saturation voltage on both sides. Okay, and coming to quickly the applications, one of the very basic application is a comparator circuit, right? That means for negative inverting input, you have given it some reference voltage, 2 volt or 3 volts, and here you are providing the input signal. in this case analog input signals, and you want to see what is the output. So if V in is greater than Vref, that means positive input is seeing a higher voltage as compared to the reference voltage, you will get plus 50, you will get plus Vsat. This is the plus VCC or plus Vsat. Similarly, if your input voltage, which is over here, is less than the reference voltage, you will get a minus Vsat, you will be over here. And this is the linear region. So when you want to operate as an amplifier, you want it here. Okay. This usually we perform using a negative feedback because it gives stable outputs. But negative feedback, I mean the output terminal which is over here, some of it is fed to the input at inverting terminal over here. You can see this through this resistor. This is also known as the feedback circuit. In this feedback circuit, I only have a resistor. So this output is being fed to the input. And this usually gives stable output. However, if the output is being fed to the input, to the non-inverting terminal, this is a positive feedback. This term is positive feedback, and it gives unstable outputs, which means is that it will quickly jump between Vsat and minus Vsat. It will not operate here. So this is unstable, but it's useless. We can use it to create waveforms, sinusoidal waveforms, square waveforms, and so on. And this is a very good application of an operational amplifier. Not just as a stable output in case of when you want amplification, but also to give the as output, we can also get a sinusoidal outputs or sawtooth outputs and so on. Okay, and our session today will be primarily focused on Schmitt trigger. It will be positive feedback and many questions on Schmitt trigger, so that we learn to analyze the circuits containing Schmitt triggers. So just a quick overview of a Schmitt trigger. So as I told you, it's a positive feedback. So you can see the output is talking to the positive terminal. All right, and this is, I'm feeding the input here. The negative feedback here is grounded, and what I'm assuming is that this diode, op amp is ideal. What this means is that input currents are zero. Input currents are zero. Okay, I'll explain it. What do I mean exactly about it, right? Okay, so since positive feedback results in unstable equilibrium, V out can only be plus Vsat or minus Vsat. Now note there is plus Vsat, which you denote like this: plus Vsat and minus Vsat. Since it's an unstable equilibrium, positive feedback is an unstable equilibrium, right? So let's take the first case in which we assume that V0 is sitting at plus Vsat. When will that happen? That will happen when this voltage V plus is greater than V minus. Then only output will be sitting at plus Vsat. All right. So let's do that now. Now analyze in this case. We apply KCL at this node. I told you is also called the non-inverting terminal. So when I apply KCL over here, this is the current I1, this is the current I2, and as I told you, input current is to be zero. This means no current can be flowing in the op amp. So this current will also be zero. Remember we talked Rin equal to infinity or mega ohms. I'm using that information. All right. So this is zero. So I1 equal to I2. Now what will be I1? If you apply Ohm's law here, so it will be V1 minus V plus over R1. What will be I2? I2 will be V plus minus V0 over R2. You rearrange the terms, you get V plus equal to, you get this expression. All right. V plus equal to V0 R1 and so on. Right. And we know V plus should be greater than V minus. What is V minus? V minus is nothing but zero. Right. So this whole expression has to be greater than V minus. And again, if you rearrange the terms, you get, and note, what's the value of V out? V out here, V out is plus Vsat. You put in all the values, you get this condition, that Vi must be greater than minus Vsat R1 over R2. For this specific circuit, output voltage will remain at saturation voltage, right, until Vi is larger than this. And we have also assumed that we are starting with V0 equal to plus Vsat. All right, so this is an assumption. The second case, when I'll assume V0 is sitting at minus Vsat, right? And what I'll do, I'll start, if it's sitting at minus Vsat, now I'll slowly start increasing the value of Vi. Okay, and I want to see when does it switch to plus Vsat. That's my aim. I want to find that voltage. Okay, again I'll apply KCL at this non-inverting terminal. Again, this current flowing will be zero, so I1 equal to I2. You again write those expressions. Again, the same expression of V plus will come naturally, but this time the value of V0 is minus Vsat. You put it, and you get Vi less than this value. Okay, so this is the complete analysis. Now let's put it into a format like this. So we saw V0 will remain plus Vsat when we start with plus Vsat and Vi is greater than minus Vsat R2 over R1. Second case, we saw that if we start V0 equal to minus Vsat, it will remain minus Vsat until Vi is less than this value. So what I'll try to do, I'll try to plot this over here. Okay, and just for the sake of simplicity, I'll assume that plus, so I'll say that this is, again, remember, this is plus vsat and minus vsat, plus vsat and minus vsat. Okay, so I'll assume that vsat equal to 15 volts. Okay, so it says that if vout equal to plus vsat, then vout will remain at plus vsat until, and let's also assume that R2 by R1 equal to 10. Okay, these are in such a ratio that R2 by R1 equal to 10. So this will give me Vi greater than minus 1.5. So if Vi is greater than minus 1.5, which will be somewhere over here, minus 1.5. If Vi is greater than minus 1.5, this means plus Vsat will remain at plus Vsat. Okay, let's draw the plus Vsat value. So if Vi is greater than this value, this means it will remain at plus Vsat, something like this. Okay, what will happen if we start reducing the voltage from Vi? So till here it's fine, we keep on reducing Vi. What will happen? It will switch from plus Vsat to minus Vsat, and we denote it in this fashion because it started very high input voltage and we kept on reducing. This is the waveform that we'll get, right? So we have plotted the first part. Now it says, and you can also see that if Vi is very much negative, then this voltage, naturally, if you apply the potentiometer rule here, then you can clearly see this voltage will be smaller than 0, right? So if that voltage is smaller, this means you are starting with a much negative. So when Vi will, if very much negative, we are somewhere over here, which makes sense. Now we want to know when does it switch. So we know if V out is minus Vsat, it's already at minus Vsat, it will remain at minus Vsat till what time? Till Vi is less than this value. This value we have already determined to be 1.5 because Vsat is 15, this value is 10. So it will remain, so again we'll start, now we'll start increasing from very large negative Vi, we start increasing, hence this arrow, again this arrow is like this, and it will stay minus Vsat till Vi is less than 1.5, it will stay like that, and at 1.5 it will switch. So this voltage is 1.5 volts, and then it will go like this. You can see it's a hysteresis. This is what is called hysteresis. There is not a single switch, it's a double switch. So when we go from low to high, it will switch at 1.5 volts. When we go from high to low, it will switch at minus 1.5 volts. This is called hysteresis. This voltage is known as VTH. This voltage is known as VTL. Okay, so these are different, and that's the key thing about Schmitt Trigger. So it will always remain at plus Vsat minus Vsat, but depending on whether you are increasing the input voltage or decreasing the input voltage, your switching point will differ. And that's the beauty of it. Now using this information, we'll just solve some problems. Okay, so this is the first problem that I have for you. So till this point, if you have any doubts, you may ask, because till now I was only talking about the theoretical part. Subir, hi, can you hear me? Till what time, till what point of time could you can you just tell me so that I can repeat myself, because I don't know when the signal broke. Apparently it was, I just checked and it was not there. So can you tell me until what slide were you able to hear about the Schmitt trigger op amp? So this slide, was it this slide, circuits using operational amplifier? Okay, previous slide. All right, I'll quickly explain. So on your screens, I've just put a comparison for between ideal and real amplifier. So there are various parameters like open loop gain. Ideally it's infinite, but it's practically it's 10 to the power 5. Similarly, output voltage can be infinite, but usually it gets saturated plus or minus Vsat, which you can see over here, plus 15 and minus 15 volts. Similarly, input impedance can be infinite ideally, but in practical terms it's a few mega ohms, sorry. Output impedance, which you can see over here, ideally it's 0, but in reality it's a few ohms. Similarly, the offset voltage I have already talked about a bit about in my previous sessions. You can go through that. The term here I can focus in CMRR. CMRR is nothing but 20 log AD over AC. As we saw in the previous slide, AD and AC, and I told you AD must be very large than AC for it to be a good op amp. So we quantified this using the term CMRR, 20 log AD over AC. So that's what I mean by that. If you put AD equal to 3 orders higher, then this will come out to be 60. If you put AD to be 5 orders higher, it will come out to be 100. And this is usually a value which you will find for the practical operational amplifiers. And this is again in a different way I'm drawing the same operational amplifier. This plus terminal is also known as the non-inverting input. Because the input, any input you give here will be in phase with the output here, which you can see from this formula also. Similarly, this is called the inverting input, because if you provide any input here, it will be out of phase with the output because you have a negative sign, you can see in this formula. So this is the summary of it. Now operational amplifiers can be used in different formats. So this is a simple comparator circuit. That is, if you are, so I'm providing input at the non-inverting terminal, and inverting terminal has some reference voltage. So if the input voltage over here is higher than the reference voltage, you will get plus Vsat. This means you are operating in this region. However, if your input voltage is less than reference voltage, you are operating in this region. In the middle is a normal linear region in which we usually operate for amplification purposes, which we achieve using a negative feedback. It gives a stable output, and negative feedback is called because output is fed to the negative terminal, the inverting terminal, which you can see over here. Examples are integrated and differentiator. Again, you can refer to the previous sessions for more details. Today we'll be focusing on positive feedback because it gives an unstable output, but it's also good positive because output terminal is being fed to the positive terminal, the non-inverting terminal. Some examples are oscillators and Schmitt triggers, which we'll talk about right now. So on your screen you can see a Schmitt trigger. It's a positive feedback circuit because output voltage is being fed to the non-inverting terminal over here, and this is the input also being fed to the non-inverting terminal. And so what I'll assume is that input Rin is very high, so that there are no input currents that are flowing into the operational amplifier. So we know that since positive feedback is in unstable equilibrium, V0 can only be plus or minus Vsat. Right. So what I want to do, let's just think about a very high input voltage, let's say 100 volts. Right. This means that, and this can only be plus or minus 15 volts. If you apply the potential divider over here, so this value will be definitely positive because this is 50. This is maybe like 100 volts, and this is sitting at 15 volts. So this will be definitely plus volts. This is V plus will be definitely higher than V minus, and we will be sitting at plus Vsat when V in is very high. Okay, now what I want you to do is, since V in is very high, now I want to find that V in at which V out will switch from Vsat plus Vsat to minus Vsat. Okay, so now we are interested in finding that case, that limiting case. So that limiting case is when V plus is greater than V minus. Alright, and here V0 will be plus Vsat. Alright, what this means is that if I apply KCL at this terminal, which would mean I1 equal to 0 plus I2. 0 is coming from here. Remember, this Rin is very high, so there is no input current to the op amp. And if you plug in the values of I1, which is Vi minus V plus, this node is V plus, by the way. This node is V plus. Potential of this node. Minus V plus over R1 equal to V plus minus V0 over R2. This is the expression for V plus, and remember V plus has to be greater than V minus. V minus is nothing but 0. It's grounded over here. We do that and we obtain that the switching from plus Vsat to minus Vsat will happen at this specific input voltage. Alright. Now we take the second case. In this case, we'll assume that this voltage is already at minus Vsat. You can assume it to be that Vi is like minus 100 or minus 50 or something. Very, very large negative voltage. And in that case, now I want to switch from, and in this case, naturally, V0 will be sitting at minus Vsat. Okay. And now I want to find out, and this is true when V plus is less than V minus. Now I'm interested in finding out that when does output switch from minus Vsat to plus Vsat. This will happen at this limiting case when these become equal. Okay. But let's just solve for this condition and we'll put the limiting case later. Again, I'll apply KCL over here. I1 equal to 0 plus I2, again assuming no current flows here, and this voltage is again V plus, this node voltage. You write this formula, again you obtain the same expression for V plus, but this time the value of V naught is minus V sat. Alright, you put in these values and you find Vi must be less than this specific voltage. Okay, so alright, let me remove this, and so this is the result that we have obtained, that V naught, remember we started for very high V in, it was V sat, and we slowly reduced V in. So let me say this, so for very high V sat, very high V in, we saw that output is plus V sat, like somewhere over here. So these are some data points, and I'm slowly reducing the value of V input, like, but till V in remains greater than this value. Let's put some numbers. So let's say this is plus 15 V sat and this is minus 15. Alright, and let's say R2 upon R1 equal to 10. Sorry, equal to not 10 but 0.1. Okay, let's operate with this condition so that you can analyze it better. So if we keep on reducing, it will remain. So this value comes out to be minus 15 into 0.1 minus 1.5. Okay, so this value comes out to be minus 1.5. Let me write it in a better way. Okay, so this value based on the value so this value comes out to be minus 1.5 volts. So this implies till Vi, so Vi switching will V out will switch from plus V sat to minus V sat at minus 1.5. Let's mark this minus 1.5 over here. So till this time V out will remain high, and only at this stage it will switch. We denote it like this, and this is plus V sat, so this is plus 15 volts. Okay, and it will remain like this throughout. Okay, now let's do this case. We saw that at very negative input voltages the output is minus V sat. So these are some data points. When it will switch, so we are operating now in this condition. This will switch at from low to high. This will switch at, this is 1.5 because V sat is 15, R2 by R1 is 0.1. Okay, so this will switch at 1.5 volts. Till Vi is less than 1.5 volts, it will remain at minus V sat. So it will remain at minus V sat till 1.5. So let's say this is 1.5 volts, and only then this will switch to a higher voltage like this. And for higher, naturally it will be over here. So this is how the output V0 by Vi, V0 over Vi looks for this Schmitt trigger in these specific cases. Alright, so you can see that the switching from low to high and high to low depends on what was the past. So it was high earlier, the switching will happen at minus 1.5. However, it was low earlier, the switching will happen at 1.5. This is known as hysteresis. This is known as hysteresis. It is as if the system remembers its past. It has some memory. It knows where it was before, and then accordingly it behaves. And this is a useful application to generate the signals. So I'll pause a bit over here, and if you have any doubts or comments, you may ask. Because then we'll then quickly jump into the problems. Alright, we'll go ahead and solve the first problem. So in this question it asks that in the Schmitt trigger circuit shown in the figure, op amp is operating at V sat plus minus 10 volts. So these are V sat, which are not drawn here, but so these are there, and we need to find what is V0 versus Vi. So in a way we are doing the previous problem again, but this time kindly note that in that time the input was provided over here. This time the input is here. So we'll analyze. So this is a different flavor, and we'll solve this problem. All right. So I have drawn this circuit here, repeated that, and we need to find V0 versus Vi. All right. So just for the first case, let's consider very large negative Vi. A Vi may be minus 50, minus 100, something like that. Very large negative. Okay. So let's just see what happens. Now, kindly note that V0 can only be plus 10 volts or minus 10 volts, right? Because it's a Schmitt trigger, and that's how it behaves. Okay, can only be plus or minus 10 volts. This means that, this implies that this V plus can be between 3 to 10 volts, because this is 3 and this is 10. So this potential has to be between that, or it can be between 3, say minus 10 volts. If it's sitting at minus 10 volts. So these are the only two cases. But remember, we are applying very large negative voltage, something like minus 50. So what that means is that if Vi is less than 0, this implies V plus is less than V minus, because V plus can only be like between 3 volts or 10 volts or 3 or minus 10. Vi is something like minus 50. V plus is less than V minus. This implies V out has to be minus V sat at minus 10 volts. So for very large negative Vi, V out has to be minus 10. This is a very important piece of information. Similarly, for case 2, let's say consider large positive Vi, that is Vi greater than 0, like 50 volts, 70 volts, 100 volts. What will happen in that case? Again, V0 can be plus 10 volts or minus 10 volts. This implies V plus can be, again same, 3 to 10 volts, because this is the potential divider. So this is 10, and this voltage has to be between this voltage and this voltage, or 3 to minus 10 volts. If this is minus 10, this potential V plus, this is V plus, can only between 3 and minus 10. And we already know Vi is greater than 0. That's the case we are talking about. Note here. This implies V plus is greater than. So in this case, V plus, V plus will be much smaller. All right. Okay, I made a mistake. So V plus here was 3 to 10 volts. V minus was very large. So V plus, yeah, correct. So that was correct. Now in this case, Vi is very large. Okay, just a second. I think I made a mistake. So V plus here is 3 to 10 volts and Vi is large negative. Sorry, then V plus is greater than V minus. Because V plus is between 3 to minus 10 and V minus is like minus 50 or minus 70. This will be plus V sat. Okay, in this case, V plus is much smaller than V minus, because V minus, which is Vi, is very large. Okay, 50 volts, 70 volts. Alright, this implies V0 must be at minus V sat, which is equal to minus 10 volts. Okay, so this is the case that I have obtained. That is, when Vi is very small, V out is at plus 10, and when Vi is very large, very larger than 0, then V out is sitting at minus 10 volts. Okay, now let's build up on this. Now let's talk about case 3. Now we'll assume that V in, okay, V in now is V out is sitting at plus 10 volts. V out is sitting at plus 10 volts. Okay, this means we are coming from, we are talking about this. We are here and we want to find out what is the switching, at which voltage Vi does this switch. Okay, if V out is plus 10, let's try to find out what is V plus. Okay, so this is a simple potential divider, and I can write V plus will be nothing but, note, no current will go here because I'm assuming Rn is very high. So V plus, we can simply write it as, okay, so let's just, I1, so this current will be same as this current. Okay, so what I can do, this is V plus, these two currents have to be the same. So I can write, this was the case 3, what was it? V out, I have assumed it to be plus 10 volts, and I am interested in finding this transition, step down. Okay, so let's apply KCL over here. No current can flow, so I1 must be equal to 0 plus I2. This is I1, this is I2. So I1 I can write as 3 minus V plus upon 1.2k. This must be equal to V plus minus V0, which is 10 over 9.1k. Okay, so let's just try to solve it. I'll take 9.1 on that side, so it will be 9.1 over 1.2. This will be V plus minus 10. So from this I can obtain V plus as 10 plus 3 by 1.2 divided by 1 plus 9.1 by 1.2. So these are the values that I have obtained. Let me quickly get my calculator to just see what are these numbers. So on numerator you will get 12.5, and denominator you will get 9.1 by 1.2, which is 7.58. You add 1 to that, that's 8.6. Okay, and this comes out to be 12.5 by 8.6, comes out to be around 1.4. So V plus is coming out to be 1.4 volts, and this means the switching here, I'm talking about the switching condition here, right? So this means V plus here is 1.4 volts. So when will switching happen? So this will remain true when Vi is, so V plus, if it's larger than V minus, we'll stay at plus V sat, right? So V plus, what is the value of V plus? 1.4, should be greater than V minus. If V out has to stay at V sat. We are interested in the limiting condition. So when Vi is greater than, sorry, is, so just a second, let me correct this. Yeah, so what's the value of V minus? V minus is nothing but Vi. Okay, this is Vi. This means till Vi is less than 1.4 volts. Okay, till Vi is less than 1.4 volts, what we'll have V naught equal to plus V sat. All right, just let me see if I've done it correctly. So I've assumed V naught equal to be plus 10. All right, so we are interested in this switching from high to low, sorry, yeah, interested in high to low. So and we put in the KCL, and then we obtain this condition will remain true only when V plus is greater than V minus. V plus we obtain is 1.4, and so Vi when it's less than 1.4 volts, this will remain true, right? And similarly you can do the case 4 also. When will it switch up? So that means V naught presently is minus 10 volts, and we are interested in finding this point, right? This will happen when, so we are currently here, so this will be when V plus is less than V minus, then only we will be in this, and we are interested in finding the limiting point. Again you assume I1 and I2 the same thing, but this time this value is minus 10, right? So let's write the KCL again. So I1 equal to 0 plus I2. Again I am assuming no current flows here. Okay, so the value of I1 can be 3 minus V plus over 1.2. This will be V plus, this is V plus minus V naught over 9.1. You solve this, this will be 3 minus V plus, this is K, 9.1 K over 1.2. Let's put the value of V naught, it will be minus 10, so this will be V1 plus 10 over 9.1. Okay, if I solve this again, V plus will come out to be, it will be, just a second, did I make a mistake there? Okay, yeah, there's a mistake. It's 3 times 9.1 actually, 9.1 times 3 over 1.2. So that's there's a mistake here. Okay, so let's solve this. So 9.1 times 3 over 1.2, 9.1 times 3, just a second, divide by 1.2, this is coming out to be 22.75. This is 10 plus 22.75. This is so it will be 10 plus 22.75, yeah, divide by 1 plus 8.58. So 9.1 divided by 1.2 is 7.58. So that comes out to be 32.75 over 8.58. Okay, 32.75 divided by 8.58, it comes out to be around 3.8 volts. So if Vi is less than 3.8 volts, we'll stay in plus V sat, and this is the switching point. Again I'll do the same here. So it will be V plus, if you rearrange the terms, it will be yeah, so V plus can be written as 1 plus 9.1, just a second, it is, let me write the numerator first. So numerator would be 3 times 9.1 divided by 1.2 minus 10. So this will go to that side, and denominator would be 1 plus 9.1 over 1.2. So again these are the same terms that we saw before. Okay, so there's nothing has changed about it. So it's 22.75 minus 10. In this earlier case it was plus 10 divided by, we remember it was 8.58. So 22.75 minus 10 is 12.75 divided by 8.58. This comes out to be around 1.5 volts. Okay, so now the switching will happen at, so now we put this condition, V plus it should be less than V minus. So V plus should be less than V minus, and then only we stay in this case. Okay, so V plus is 1.5 volts, V minus is nothing but V in. So this is true only when Vi is greater than 1.5 volts. Alright, in the other case we saw Vi must be less than 3.8 volts. Okay, so what we saw was that in the case 1, if you remember, we saw that, so this is V out, this is V in. what we saw, if you remember this case, if for very large negative Vi, the output was plus Vsat. Okay, so for a very large negative Vi, this means something over here, we got plus Vsat, so we are here. For very large positive Vi, we got minus Vsat, so we are over here, right? And we saw that two switching points were 4 point so this was 1.5, so switching to top was 1.5, this means this is 1.5 and the other voltage was 3.8, this is 3.8, switch down. So this is how the waveform it looks like, and this closely matches our option B. You see, this is high here, low here and low here, and the switching happens in this way, which is the question over here. So that's how we solve this. Just to quickly summarize, you have to figure out what happens at very high and very low voltages, and then you find out the switching points, right, which we did using applying the KCL over here. And so this is how we solved it. And in the second problem we asked what is the VTH, the same problem as before, just we are required to find the VTH. Okay, so what do I mean by VTH over here? So if you see that we have already solved for VTH, this is the VTH, the high trigger VTH, this is the VTL, right? So we simply saw that how to find VTH. We apply the KCL at non-inverting input. I'm not going to do the analysis again, you can refer to the previous slides. KCL at non-inverting input, and then you evaluated, so no current flows here, I1 equal to I2. We did that and we have obtained that VTH was 3.8 volts, right? So yeah, so that was that. So this was 3.8 volts, something like that. In problem 3 now we are required to find the VTL. So how do we know that? From Q1 we know V0 switches at, this is what I am talking about. So remember, this is how it looks like. So this was VTL, this is going like this. Okay, so this was VTL, and VTL we evaluated switching from minus Vsat to plus Vsat. This is what I have written here at Vi equal to VTL, and we saw that this potential was 1.5. Yeah, so this was happening at Vi equal to 1.5 volts. This point was 1.5. So this implies VTL equal to 1.5 volts. Again, the analysis is through KCL, which we have already done. So what happens is option D is the correct one. Okay, so this completes these sets of problems. If you have any comments or questions, feel free to ask, because now we are going to switch to a different problem. But the concept remains very simple. You just need to make sure that what happens at very low voltages, firstly, secondly what happens at very high voltages, and when does the switching happen. So these are the only three things you have to keep in mind. And since Rin is very high, we'll assume no current is flowing. So it's just very simple, just KCL at just one single node and nothing else. Okay, so now moving on to the next question. It says that in the Schmitt trigger shown in the figure, the op-amp is operating at plus minus Vsat equal to plus minus 12 volts. So this is plus 12 volts, this is minus 12 volts. We are required to find upper and lower trip points, so VTH and VTL. So these are also called the trip points. So this is the upper trip point, and this is the lower trip point. Okay, so this is the circuit, and we are required to find the upper and lower trip points. As I did before, consider very large negative Vi. Okay, when this is very negative, like minus 50, minus 70 volts. So what will happen then? Again, remember that V0 can only be plus 12 or minus 12 volts, correct? This is the only possible values for that. So this implies that this is the potential divider essentially, right? If we apply very large negative Vi on very large negative Vi, V plus will also be negative, very negative. Why negative? Because you can see that the potential here is dividing in ratio 1:5, right? If that is happening, it's only being divided in the ratio 1:5. If you apply it minus 20 or minus 100, let's say, and if it's even if it plus 10, this value, if you see, will so this will be divided in 1:4 or 1:5, something like that. So it can never, it will always be negative, something like minus 90 or minus so yeah, something like that. It will be negative voltage. So, and this, from this I can say that V plus, it will be less than V minus, because V minus is 0, right? This implies if V plus less than V minus, this implies V naught will be equal to minus V sat. All right. So this is what this is how we'll see for a very large negative Vi, V naught will be minus V sat. And similarly, I'll draw a similar case 2. In case 2, consider large positive Vi, that is Vi greater than 0. Again, V naught can be plus 12 or minus 12 volts, and this would mean V plus will be in the range of, this is very large positive, let's say maybe 100 volts, right? So this can be between 12 to 100 volts, and this will be minus 12 to 100 volts. And if you apply the potential divider over here, right, yeah, sorry, if you apply the potential divider, so this is a positive value, and this will also come out to a positive value, because so if this is minus 12, right, and this is 100, then you do the calculations, you do the potential divider like R2 over R1 plus R2, and you will see this will also turn out to be a positive number, right? So from this we can see that V plus will be positive, which is greater than V minus, which is 0. This implies V naught will be plus V sat. So these are the qualitative analysis. We are not going too much into quantities. I'm just doing a very hand wavy assumptions, because I'm assuming it to be very large, and I know due to the potential divider this value will also turn out to be positive, because this is a very large positive value, and thus V out will be plus V sat. Okay, so now we know this much information. Now we'll go ahead, and so what we know is that for Vi very negative, V out should be minus V sat. So what I'll do is that I'll just draw this diagram. Okay, this is Vi, this is V naught. For very large negative, this should be minus V sat, and for very large positive, this will be plus V sat. So this is plus 12, this is minus 12. Okay, so that hysteresis will be happening somewhere over here, correct? And if I consider the case 3, that was, we'll assume V naught is sitting at plus V sat, and we are interested in finding this transition, right? So we are here, and we are interested in finding this transition. So that is V plus must be greater than V minus. So this is what we are interested in. And if you go through the very first theory part in which I solved the problem, so I'll copy the result. But what we got was, so where was it? Yeah, it was here. So in this case, we have assumed V naught equal to plus V sat, right, here, and we saw that Vi must be greater than this quantity, all right, minus V sat R1 over R2. So the analysis remains the same, so it doesn't change. So I'll just copy paste the same result over here, just a second. Yeah, so we saw that it does it for when Vi should be greater than minus V sat R1 over R2. So only then it will remain here, otherwise it will switch. So let's just put let's just see what this number comes out to be. Minus 12 times R1 is 1.5k over 6.8k. okay, so this number comes out to be, just let me get my calculator, 12 times 1.5 over 6.8. this comes out to be around minus 2.65 volts. So till Vi is greater than this value, it will remain at plus V sat. This means the switching is happening at, this is minus 2.65, switching is happening at this particular. So we are here, we keep on moving left, it will remain high, and only at minus 2.65 it will switch, and then it will remain like this. So we have completed the first half. So this is what is VTL. This gives me VTL equal to minus 2.65 volts. All right. Now in the case 4, when we'll assume V naught equal to minus V sat, that means I'm talking about this transition. Okay, here I'll say V plus must be less than V minus, that is I'm operating in this region. And again, if you put in the same formula, there we saw Vi must be less than plus 12 times 1.5 over 6.8k. If you go back, just the sign changes, right? So this gives me Vi must be less than 2.65 volts. So till Vi is less than this value, 2.65 is somewhere over here, it will remain at minus Vsat. So this means it will continue to be minus Vsat. So when we are coming back, this is the condition when we are coming back, and it will switch only here, and then finally it will continue to be like this. So this is how the hysteresis will look like. Sorry, this is happening at, so this is minus 2.65, not this. Okay, this is the plus 2.65 somewhere over here. Let me draw it again. So this is plus 2.65, it's happening over here, switching is happening over here. Okay, so this is how we solve these problems. Again it's very similar to before. We analyze what's happening at very large negative, very large negative, very large positive, and then we see when the switching is happening. And this I noted using case 3 and case 4. We have already derived the formula before, I just simply used it. So our answer is plus minus 2.65 volts, which happens to be our option B over here. All right, so this is again a very straightforward problem that we had solved. Now the next two sets of problems are again just an advanced version of the problem which we had solved before. So these diodes are added. We'll first discuss the role of this diode, but let's just read the problem. In the Schmitt Trigger circuit shown in the figure, op-amp is operating with plus minus Vsat equal to plus minus 15 volts. So this time it's plus 15 and this value is minus 15. The Zener diodes have Vz equal to 9.3 and V1 equal to 0.7. Okay, so this is interesting. So Vz, this means, let's say these are conducting, right? So this means this will be in breakdown. If this is in this direction, this is on, this is in Zener breakdown, then only these will conduct, correct? Hence the total drop will be 10 volts, which we'll analyze a bit later. What are the upper and lower trip points? So we know the definition of those trip points, right? So it will look maybe something like this. Sorry, so like this and then like this. Okay, right, because the nature image is the same. If you see from the previous problem, the nature is exactly the same, except we have some diodes over here. So nature, the way it behaves will remain the same. Okay, so in this case again we'll just analyze what happens at very large negative and very large positive voltages. Okay, which I have already done that. So I'll not go over it again. So what we had noticed in the previous question also. So in the very large, so in the very, when Vi is very large negative, it will be minus Vsat. Okay, so I'm going to use that same information over here. So what I mean is that it will look something like this in these regions. This is V0, this is Vi, this is plus Vsat, plus 15, and here it's minus 15 volts. Okay, we are interested in finding this when the switching happens, when the tripping happens. Okay, all right, so now this is my case 1. So I am assuming V01 equal to plus Vsat. All right, so what that would mean is that now let's label some voltages. So this is V plus. Okay, this means that when it will be Vsat, when V plus is greater than V minus, then only it will be at plus Vsat. So V plus is this, V minus is this. All right, so now let's quickly just have a quick look at this, only this part of this circuit. Okay, if V01 is sitting at plus Vsat and this terminal is ground, just only look at this circuit. So what effectively happening is, this is at higher potential, this is at a lower potential, current will tend to flow in this direction, correct? Like somewhere over here, right? So sorry, current will start to flow somewhere over here, right? Because this and so this would mean is that D1 is forward bias and D2 is reverse biased. Now in order for the current to flow, D2 should not only be reverse biased but in Zener breakdown mode. So I'll write that. In order for current to flow, D2 must be in Zener breakdown mode, because otherwise if it's not in Zener breakdown mode, there'll be very small amount of current. Remember, this is how the characteristics of a Zener diode looks like. So this is the Zener mode. This is forward. This is I versus V. Okay, so we are operating either here or here. So D1 is here, D2 is here. So D1 is here while this is D2. Let me make it a bit better. So this is Zener breakdown mode where D2 is operating. Okay, so how will the circuit then look like? It will look something like this. This is V0. This will be a plus 0.7 drop because that's given in the problem, and again a 9.3 drop. That's the Zener breakdown voltage. So the total drop from here to here would be, and this is your R3 and your V01. I'm not drawing the other circuit, remember, I'm only drawing this part, the blue rectangle. So what will happen is that this gives us that V0 equal to plus 10 volts. So, and the VO1, which is the output of this operational amplifier, is at plus Vsat. V0 is at plus 10 volts. So this is the critical piece of information that we had obtained. Okay. So now let's try to use this information. Let's try to use this information over here. V01 is equal to plus Vsat. Then Vout equal to plus 10 volts. This is at plus 10. This is V plus. Okay. Now simply using the potentiometer, the potential divider over here, I'll try to find the value of this V plus. Now this we had already seen before, right? This same formula, that because what we are doing is I'm switching from here to here. Okay. This is what I'm doing, but in this case the value is just 10 volts. So we saw that formula. That formula was Vi must be less than where was it? Yeah, this one, minus Vi must be greater than minus Vsat R1 over R2. So that comes out to be Vi must be greater than, so in this case this Vsat, the circuit was not there, so in this case it will be minus 10 because this is being fed to the non-inverting terminal. Earlier it was this output directly, right? But in this case it's this plus 10. So it will be minus 10 times, this will be 1.2k over 8.2k. So Vi must be greater than this value. So again I'll just write this here for the sake of completion. This will be true only when V plus is greater than V0. Hence the Vsat here will not be Vsat. Okay, it will not be Vsat in this formula which we had derived earlier. It will be V0, this voltage. Okay, if we solve it, it's 12 over 1 so it will be 12 over 8.2, which comes out to be 1.46. okay, so this means this tripping from high to low will be happening at Vi equal to minus 1.46 volts. Okay, right. So now let's solve for the second case in which VO1 is minus Vsat, or we have already solved for Vi equal to plus Vsat. Again, if you just look at this rectangle, just look at this rectangle first. So what's happening? This is sitting at minus 15. Minus 15, yeah, this is sitting at minus 15. So if you see, the current will start to flow. This is at a higher potential, this is at lower potential, so current will start to flow in this direction. Okay, so what would mean is that this would mean that D2 is forward biased and D1 is reverse. But the current will flow only when D1 is also in Zener breakdown mode. So D1 is in Zener breakdown mode. Okay, then only the current will flow. All right, and in that case what would happen? The circuit will look something like this. This is V0. So this is in reverse breakdown mode, right? So what's going to happen is so it will have a drop of minus 9.3 in this direction. So this means it will have a drop of 9.3 in this direction. Similarly, this below one is forward bias, so that will be a 0.7 volts drop, and the rest of the circuit will remain the same. This is R3, this is V01. I'm not drawing the other part of circuit. So with that, so you can clearly see V0 is nothing but minus 10 volts. Earlier, if you see, it was coming out to be plus 10 volts. Okay, so now we have obtained V0 equal to minus 10 volts, and again this is V plus. So if we again do the KCL, and we have already done it before, so I'm just using the formula directly. So again, this case is true when V plus is less than V minus. Okay, this is the same. If you apply the KCL and apply this inequality, so you will get the formula that Vi must be greater than V0 times R1 over R2. we had derived this earlier. So we put the formula, that is 15, sorry, the values. R1 is 1.2 over 8.2, and this will give us V0 should be greater than 1.46 volts. Okay, so now let me draw. So okay, we have obtained the tripping point is 1.46 volts, but if we wanted to, let's say, just to draw the how that will look like. Okay, we saw that a very high Vi, it was here and it was here. This is V0 versus Vi, and then the VTL was minus 1.46, so it trips like this. This is minus 1.46, this is plus 15 and minus 15, and the upper tripping point is somewhere over here, and this point is plus 1.46 volts. Okay, and that's again nothing, I'm just doing nothing new, it's just that this is acting as a voltage regulator. So rather than going to plus 15 or minus 15, the output voltage will be stuck to plus or minus 10. That's the only thing we saw, and that happened due to this property, right? It's in forward bias or in xenon, otherwise it won't conduct. Okay, so that's how we saw this property, and the direction you can also note over here. Okay, so the next problem related to the same problem is that what is the minimum value of R3 that is required such that op-amp current is limited to 5 milliamps. So let's so we are required to find the restriction on this fellow, right? Such that the output current, so output current here is something like this. This is I, it's noted by I naught, I output, right? This should be restricted to this should be restricted to 5 milliamps magnitude, right? So I op amp should be less than 5 milliamps, so which I'm denoting it as IOA. Let's say there also I'll say IOA. Okay, so we saw in both the cases. So in the case one that we saw, what we had seen was that this was sitting at plus 15 volts, right? This was sitting at plus 10 volts. If you remember, this was R3, this was V01, this was V0, correct? And IOA is nothing but this. Simply, what's IOA? You apply the Ohm's law here, so that will be V01 minus V0 over R3 equal to I naught A. This should be less than 5 milliamps. Simple. This will give me R3 should be greater than equal to so let's put the values, 15 minus 10 over 5 milli. So R3 should be greater than equal to 1 kilo. Okay, 1 kilo ohms. And in the second case, what we had was, this was at minus 15, this was V01, this is again R3, this was V0, this was sitting at minus 10 volts. Again I'll assume IOA is flowing here. If you again apply Ohm's law, V01 minus V0 over R3, which is IOA, should be less than equal to 5 milliamps. That's the condition. You put the values, minus 15 plus 10 over R3 should be less than equal to 5 milliamps. You solve it. Okay, we have talked about the magnitude has to be smaller. Okay, so there is a mod over here. All right, if you solve this again, it will be 5 upon R3, and again you will get R3 greater than equal to 1 kilo ohms. So in both the cases, R3 should be greater than equal to kilo ohms. So R3 minimum value should be 1 kilo ohms, because remember we obtained R3 should be equal to 1 kilo ohms. So at minimum it should be 1K, which is option A. This is just an extension of the same problem before. So that's the utility of actually this diode, the limiter circuit that you see over here. Okay, that's an application. By using this and choosing an appropriate value of R3, you'll be able to regulate the current that's flowing in or out of the op amp. Because remember, these op amps are also rated. They have some voltages, right, and some currents. So that's the way to go ahead. Okay. Now jumping to these next 6 problems are rather together, so it's just one big whole bunch, and then we'll solve them. Okay, so the question says, which of the following statement is true about the oscillator circuit shown in the figure? So the problem says this is an oscillator circuit and we want to solve it. Okay, so it says that, so the questions asks us to predict the waveforms of V01 and V02, right? So let's do that. So this is the circuit. Now since there are two op amps, these are called stages also. This is on the left is the first stage, this is second stage. So I'll break it down. Okay, you look at the first stage in the blue rectangle over here, which I have drawn over here. This is nothing but an integrator. We have seen this in the previous classes. Okay, and on the other hand, the right side, which you can see in yellow, is nothing but your simply Schmitt trigger. See, this is the similar behavior that we have been seeing throughout. So what I'll do, will solve them independently of each other. Okay, so first, because we know how Schmitt trigger operates, right, we know the expressions directly. So what I'll try to do is that we'll try to predict the behavior of this fellow V02. Okay, and this is the input that is coming to it, right? This is nothing but VO1. So we know the expressions for this. We have been doing this for now 4 or 5 problems. So it looks something like this. This is V out. So in this case it's V02. This is the input, which is V01, and we know how the behavior will look like, right? We have been seeing that. So at high voltages it is high, and at low voltages it is low, and it switches something like this, right? So that's what's happening over here. Okay, now so this is the nature of it looks like. Now in terms of V01, so what I can also draw is that you can see that it's either low or high. There are no middle stages. What this means is that essentially, alternately, we can say that V02 is a square waveform. Why I'm saying that is that square waveform, which looks something like this, has only two levels, right? In this case, one level is this, other level is this, right? A triangular waveform, which looks something like this, will have multiple V out values for a given input, which is not the case here, right? So this cannot be. A sawtooth input again will have multiple values. You can see on this edge, which is also not the case here. It only has 2 levels, this and this. It is denoted by this and this over here. So this is with respect to time, by the way. Okay, these are with respect to time. So none of them match. Okay, so those were the options that were given to us. You can see for V02, it's a square, triangular, or sawtooth. So we by the way of elimination, or just you can see even by the analysis, V02 is a square waveform. All right. So now let's look at the integrator circuit. So remember, this was V02. This is the output V01 over here. So this we know is an integrator circuit. All right, and we also know that V02 looks something like this. I'll draw V02 over here. That's good enough. So let's draw that this is V02, and this is the time axis. This is the time axis. Okay, this is how it's happening, and I want to know what's the VO1. Okay, how does it behave with respect to time? All right, since we know it's an integrator circuit, okay, first question can be, how do you know this is an integrator circuit? Now there's a quick way of doing it. Again, we'll assume no current is flowing over here and here, right? And you simply apply the KCL over here. So let's, I1 current is flowing here, I2 is flowing here. So I'll say I1 equal to 0 plus I2. Now I1 is nothing but, okay, this is by the virtual ground, by virtual ground. So note that this is the negative feedback circuit, right? So the virtual ground analysis is applicable. So I1 can I simply write as a V02 minus 0 over R. This should be equal to I2 will be nothing but, so the current through a capacitor is nothing but dCV over dt. So I2 I can write as d CV over dt. V is nothing but 0 minus VO1 over dt, right? So if I do that, so if you solve, C is a constant which comes out, right, and negative also comes out, so you will have dVO1 over dt equal to VO2 by RC with a negative sign. Okay, so minus VO2 over RC, and if you integrate it, so now what you can see, VO1 will be nothing but minus VO2 over RC integration of dt plus some constant k. Okay, so that's why we call it an integrator circuit. All right, that's why it's called an integrator circuit. So let's do that. So in this case, when VO2 is some negative value, okay, we do know the value of for that negative for that matter. So yeah, no, okay, in this example we don't. So what we know is that it's an integrator circuit, right? So VO2 is some negative, so let's give some numbers. Let's say it's minus 15 volts. So when you put in minus 15 over here, and RC is a positive constant, so what will happen is that this slope will come out to be positive. This is negative number, right? In this region I'm talking about only in this region, right? So this value, this number will turn out to be positive. So this means V01 will have a positive slope with respect to time. Okay, so this would mean is that V0 will start to rise. I don't know when it will cross 0, but it will keep on rising. At this point, V02 will switch to some positive value. This means this value will turn out to be some negative. And the slope, this is a constant, this will come out. So it will be minus some A times T, where A is a constant. This is a negative slope. So till this time, it will be a, something like this, it will be a negative slope. Again, when this turns out to be minus 15, this is plus 15, let's say. Again, it will turn out to be negative. So V02 will turn out to be negative. This whole quantity will be positive. It will be a positive slope with respect to time. Something like this, right? This is like this, and then negative, and then again positive. Okay, so you can see that, and naturally if you integrate a square wave, you will get a triangular wave. So that's the lesson that, I explained it. This is a fairly common knowledge. All right, so we skip that. So we saw that V02 is a square waveform. So square waveform and square waveform. So this is wrong and this is wrong. V01T, which is the output for this integrator, we saw it's a triangular waveform. So option C is the correct one. Okay, so the way we solved this problem was very straightforward in the sense that we broke this problem into two problems, left and right. Right we know is a Schmitt trigger, left we know is an integrator. Schmitt trigger we know can only give, in this case especially, can only give two values, right, high or low, which is representative of a square waveform in time domain. A triangular will have many values, this value, this value, this value. It's not the case here. Similarly, sawtooth will have many values. It's not the case here. So hence we concluded that this is a square wave. And when you integrate a square wave, which we saw why does this circuit integrate? I solved this over here. And then we saw that V01, when you integrate a square wave, you will get a triangular wave. Simple as that. So that's what we solved, and hence the option comes out to be option C. So that's about that. Now building on this problem, now it says that Vsat is plus minus 15 volts. So in this, now we have qualitatively, we have just seen qualitatively, that's a triangular waveform. Sorry, V02 is a square waveform, V01 is a triangular waveform. Now we want to just put in the values, how do they look like? And in this specific case, we want to obtain what is the oscillation frequency. Okay, so this is the problem that we have, and now I'll draw these waveforms again. Okay, so it was something like this. Okay, this was V02, and we saw this was V01. We just saw that, right? I'm just drawing this again. So we saw this was rising and then falling and then rising and then falling again, and this will be some time axis. This is also a time axis. Now what is the frequency of oscillation? Now it's fairly simple to see that this is the frequency of oscillation from here to here. This is one complete time period, or from here to whatever you want to, however you want to see it. Okay, so how do we find that out? We find that out when we evaluated this. Remember, V01 we evaluated. V01 was minus V02. What was the expression again? Sorry, V02 over RC dt. We'll drop the constant k term because that will get subtracted anyways. Okay, so if I do that, and now let's try to put in the value. So V02, let's say in the case 1 where V02 is minus 15. Okay, here V02 is minus 15 volts. So if I do that, V01 will come out to be, that's plus 15, and that's some time RC. Okay, and so what I'm talking about this time. Let's call this time T1. Okay, so V01 will be 15 by RC times T1. That will be the value over here. Correct? So this will be a total swing rather, the value of V01, right? Correct? Yeah, V01 will have total swing of this much, because it will start from somewhere over here and will end over here. So this is the total swing that it will see. Similarly, when V02 is plus 15 volts, this means we are talking about this time over here. This will be the total fall. right? And then again you will see that V01 in this case, I should rather say delta V01. Delta V01 will be minus 15 over RC times T2. Okay, because you see, if you put the value of V01 as plus 15, which is here, minus 15, which is here, this is the total swing that we are going to see. Okay, and now we can clearly see that this is time T2. But you can clearly see that the total swing delta V01 plus delta V02, now that so in the magnitude wise they have to be equal, right? Because these are symmetric. Okay, so in that, so from that, if you equate their magnitudes, that they will come out to be T1 equal to T2. Okay, but let's just see that algebraically. So what's going to happen with them? Okay, so let me just put the values in over here. So that will be so I can see that, just a second. So 15 over RC. Okay, yeah, so the waveform is symmetric. It doesn't look symmetric, but it is symmetric because this was symmetric, and hence this also has to come out symmetric because just an integration. Okay, so what I can clearly see is that whatever this value is, okay, let's call this Vm plus Vm, let's call this value minus Vm. Okay, so what I'm going to claim here is, just a second, let me see if I have done it. Yeah, so what now I'm going to claim is, so we see that the delta V01 magnitude of it, right, is coming out to be 15 over RC times what was the value, T1, right? And you can clearly see that the input swing that is happening for this, right, the input swing that is happening for this, it is restricted to plus or minus 15 volts. Okay, so that is the swing that has been restricted to it, and so V01 will also be subject to plus or minus 15 volts, because that is the limit that we are putting on this op-amp, on op-amp 1 also, right? So Vm, whatever the Vm is, right, will have to respect that value. Okay, so I can see total swing is 15 by RC into T1. Okay, this swing will be written as 2 Vm equal to 15 by RC into T1. Vm is nothing but plus 15 volts, so this will come out to be 30 equal to 15 over RC into T1. Okay, this will give me T1 equal to 1 over 2 RC. All right, so now let me just quickly solve this, what it comes out to be. 1 over 2 RC, R value is 5 times C value is 0.2. Okay, that comes out to be very simple value of 1. So it turns out to be 1. So let me just 1 by 2 into 5k times 0.2 micro. This will turn out to be 1 by 2 into, this will be milli. So this is turning out to be around 500. So milli will go up, so it will be 500. Yeah, it will be 500 seconds. Similarly, because the form remains the same. Okay, so T2, remember the expression for it, the T2 was also the same. So what I have done essentially said is Vm is also has to be plus 15, and this is minus 15 volts. Okay, so it's 500 seconds. Similarly, T2 will also come out to be 500 seconds. Total time period T equal to T1 plus T2 equal to 500 plus 500 seconds, turns out to be 1000 seconds. And if you convert it to frequency, which is 1 over T, so which is 1 over 1000, so it comes out to be 1 second, it comes out to be, I think I made a mistake somewhere. Let me just hold on a second, I'll try to figure it out. So in the problem weight, we are required to find the oscillation frequency. Okay, so what I did essentially is that, so this we just evaluated the waveforms that we have. Okay, so the swing can be minus V0, this was the expression, minus V02 over RC times TT. All right, V02 was swinging, this was the V02 swing. So when it was minus 15, so I put minus 15 here, it will be 15 over RC times T1, that is the total swing that it will have from in this part. All right, so in this part it will have total swing of this much. So delta V0, because the delta V0 now can only swing between plus and minus 15. all right. So this will be 30 volts. So this will be so that's why I put there. So 2 vm is 30 equal to 15 over rc times t1. So if I evaluated that, so if I evaluated it, it will come out to be t1 equal to 500 seconds, and t2 also comes out to, just let me cross check it again. So 2 times 5k times 0.2 mu, so that will turn out to be, yeah, so that is correct, that is plus minus 15. So that will come out to be 1 times milli, so 2 milli will go up with 1000 by 2 is 500 seconds, so total will be 1000 seconds. Yeah, I don't think okay, I found it. Okay, sorry about that, very stupid mistake. So we saw that delta v01 it was 15 over rc times t1. Okay, if we do that, delta v01, the total swing, so that was 2 vm we saw, that was 15 by rc times t1. So this will give me t1 equal to rc over 15 into 2 vm. Now vm value is 15, so rc over 15 times 2 times 15, so this gets cancelled, so it will be twice of rc. Right, now let's me put the value of r and c. This will be 5k times the value of c is 0.2 microfarad. Okay, so this will turn out to be 1, so this will turn out to be 2 milliseconds. Yeah, 2 milliseconds. Similarly t2 will also turn out to be 2 milliseconds. So the total time period will be t1 plus t2, it will be 4 milliseconds, and frequency we know is 1 over t, so that's 1 over 4 milliseconds. So that will turn out to be, just a second, again an option is not matching, sorry about that, turns out to be 250 hertz. Yeah, I don't think any option is matching. Maybe if I multiplied by 2 pi, that might be the difference. 2 pi into 250 comes out to be 500 times 3.14. Yeah, so I think there is some calculation mistake on my part, but that is the way to do it. So the approach is remains correct, in the sense that we have v02 which is over here over rc, and we know that it's only going to swing, this swing can be maximum between plus and minus vm, so that's what we are restricting ourselves to. Okay, if we do that, and we know the maximum swing is delta v01, which is 15 over rc times t1. T1 is the rise time, you can say. So if we do that, this will be 2 vm, so it will be, and then you put in the value, so this will be 2 rc, and rc if we put 5 times 0.2, so this will turn out to be 1 millisecond, so that turns out to be 2 milliseconds. And t1 if it's equal to t2, which is the case here, because rise and fall is absolutely the same, so overall it's 4 milliseconds. Okay, and so that's how we obtain that, and then you put in the values and we obtain that this is coming out to be 250 sorry, was it, yeah, 250 hertz, but the correct answer according to my calculations I did earlier was t. So there is a calculation mistake for sure, so sorry about that. I'll try to just give me a minute, I'll try to sort it out again, that where is the mistake being made. If you point it out, if you can see, please point it out so that I can correct myself. So that's v02. Just give me a moment, I'll try to find it out again. Okay, yeah, I got it. So there is a conceptual thing that that mistake that I made. Okay, so what you see here is that when will v02 switch? v02 will switch when v01 arrives at a specific voltage. Okay, what is that voltage? So this vm which I put here is wrong, it's not plus 15. We'll see in a minute why. Okay, so we know that switching the voltage at which it switches, the VTL or VTH. Remember, we have obtained an expression of VSAT R1 over R2, right? So let's put that 15 times. So this is the magnitude actually. So VTL or VTH. This turns out to be 1.2 over 6.8. Okay, so 15 times 1.2, 15 times 1.2, sorry, 15 times 1.2, yeah, divide by 6.8, this comes out to be 2.65, which we saw in the previous problem. Actually this was 2.65 volts plus minus actually. So the switching, the V01, so switching will happen at when V01 is 2.65 volts and at minus 2.65 volts. So what this means is that this value maximum is 2.65 and this value minimum is minus 2.65. Now I'll apply the same analysis. Okay, what do I mean by that? We know that the swing in this has to be equal to 15 over RC times T1, and this maximum swing can be from minus 2.65 to plus 2.65. That will come out to be 5.3 equal to 15 over RC times T1. So T1 from this will come out to be RC times 5.3 over 15. So let's put the value 5 into 0.2 microfarad times 5.3 over 15. So that turns out to, this is 5k, sorry, 5k, that turns out to be 1 milli. So 5.3 over 15 milliseconds. So 5.3 over 15, that turns out to be 0.35 milliseconds. Okay, similarly, so similarly T2, because the form remains the same, so T2 will also be 0.35 milliseconds. So total time T will be 0.7 seconds. Frequency is 1 over T, 1 over 0.7 seconds, sorry, seconds or milliseconds, 0.7 seconds. So this will turn out to be 1.43 kilohertz. 1 over 7 is around 1.43. So yeah, so that comes out to be 1.43, which is the option D here. So the mistake that I had made was that I had assumed that this will go earlier, it will go on to plus 15. That's not the case. Switching will happen as soon as it crosses the VTH and VTL thresholds. Remember these. So these values were 2.65 and minus 2.65, assuming these are plus minus 15. So that's about it, and so we have obtained this expression, and yeah, so this is the way to do it. All right, now for the next problem, what they say is that now R1 is changed to 1k and everything else remains the same. So what is the oscillation frequency? So to do that, we just need to evaluate this expression. Okay, I'll write this expression over here again. So it was delta V01 was 15 over RC times T1. Okay, so delta V01 was the swing, right? And how did we obtain the swing? This delta V01 was nothing but VTH minus VTL. VTH we saw was VSAT R1 over R2, and this was minus VSAT R1 over R2. So this turns out to be 2 VSAT R1 over R2. Let's put this value here and let's see what the expression comes out to be. 2 VSAT R1 over R2 is equal to 15 is nothing but VSAT. So let's put 15 again over RC times T1. This gives me T1 equal to VSAT gets cancelled. This gives me 2 RC times R1 over R2. So that's the value of T that I have gotten. T1, sorry, 2 RC, I'll get R1 over R2, right? And we also know that T2 is also the same, T2 equal to T. So T equal to T1 plus T2, which is nothing but T1 plus T1. So this T comes out to be 4 RC times R1 over R2, and the frequency is nothing but 1 over time, simply just come out to be R2 over 4 RC times R1. So this is the expression for this problem. All right, now we'll just plug in these values and we'll find out anything that we want. So I'll just write it again. F equal to, that was, sorry, R2 over 4 RC times R1. So what's the value of R2? R2 is 6.8 K. 4, the value of R remains 5K, C remains 0.2 microfarad times R1. R1, now note, it has changed to 1K. This is 1K, right? Earlier it was 1.2K. Okay, so if I try to solve this, so let me do that. So this was coming out to be, 1 second, yeah, so it was like this, and now we have replaced 1.2K with 1K. Okay, so this is turning out to be around 1.71. So this value is coming out to be 1.71 kilohertz, which is option B. All right. So what impact will changing this will have, it will shift VTH and VTL. Remember, as we saw, it was formula like VSAT R1 over R2, right? So so this means the VSAT is shrinking. The maximum, the VTL and VTH swings are shrinking. This means the Vout1 is shrinking, and hence you are switching faster essentially. So that's, you see the frequencies increases. Earlier it was 1.4, now it's 1.7. Now in this case again we are changing the R2. All right, so let's write the expression. So frequency, remember, was R1 over 4 RC times R2. So now you have changed R2 to 10k. So this is not 6.8, this is now 10k. So what will happen? So again I'll just reuse the result here. So it was 1.4 kilohertz here when it was 6.8k. Now it's 10k. I'm just using the unitary method here, nothing else, so that we save some time on calculation. So it was 1.4 times 6.8 by 10. You can also put in this formula and try to solve this out. The answer will remain the same. That's not the concern here. I just want to spend some time on analyzing the results. It's coming out to be 952.95 kilohertz, which happens to be I have made some approximations. So just a second, which one has increased? So what was the formula? R2 by 4 RCR1. Okay, sorry, that was a mistake. So its frequency is R2 by 4 RC times R1. You put these values, this is 10k. Okay, so 10k upon 4 times 5k times 0.2 microfarad times R1 is 1.2k. You plug all these values, and so earlier it was like 1.4 and now it has increased to 10 and from 6.8. So this is coming out to be around 2.06k. This expression evolves to 2.06k. Again, this makes sense. How this makes sense? Since you are increasing R2, remember the VTH or VTL, their magnitude was VSAT R1 over R2. Okay, so what you are doing is that now since you are increasing this value of R2, okay, when you're increasing the value R2, you're shrinking the range on which it can swing. That is the range in which the VO1 can swing. Remember, VO1 was limited by plus minus VTH, right? So what we are doing essentially, when we are reducing when we are increasing this, we are reducing that limit of swinging. This means that V01 will achieve the requisite voltage faster, right? Because the rate doesn't change. The rate change is 1 over RC given by 1 over RC slope. Remember, slope was something VTH over RC times T. So this slope has inverse dependence on R2. So that value will be achieved faster, and thus we'll see an increase in frequency of 2 kilohertz, 2.06. So C is the closest option, which is fair enough. Now what we have done in this problem, we have now changed R. So let me write the expression again. So frequency was R2 over 4 RC times R1. Again, you put in all the values. I'm not going to let me just write it for the sake of completion. So this, now what we have done in this case now this R has changed to 8.2k. So this resistance has increased, and first we'll evaluate the expression, and then we'll analyze that how does it impact the circuit qualitatively. Okay, R1 is 1.2k. okay, so it was 1.4k earlier. Now let's see how does it come out to be. So let me get my calculator. So it's 1.4 sorry, yeah, so this is, we multiplied by 5 and we divided by 8.2. so this comes out to be 0.853. okay, 0.853, right? So this comes out to be, one second, there's a mistake, 1.42 times 5 by 8. Yeah, it's coming around 0.870 kilohertz, which you can see 870 hertz. Let's just see what's the option. 870, okay, 864. So that's the closest one, right? So what's happening is that, what I mean is that if you remember that V01 the delta v01, right, was the slope was coming out to be something like v sat over rc. This was the um, uh, this was the uh, this was the expression, because remember it increased like this, and then this. So this is the slope. So what you're doing is that when you're increasing the resistance, so you're changing the slope. So when you in this case, when you increase the resistance, right, so the slope changes, slope reduces. So this means it will rather than going like this, I'll denote it like this, it will go much more gradually, but it has to reach at the same point. This is v01. It has to reach at the same point, so it will reach at a much slower, it will reach at a much farther time, and hence your time period increases. If your time period increases, your frequency decreases. Remember earlier it was something like 1.4 kilohertz. Now it has reduced to 870 hertz, because we have reduced the slope, so it's much more gradual. Okay, so that's what it qualitatively means. So finding out answers is not the complete thing that we are trying to do here. We also want to understand what goes behind these numbers. Okay, so that's that. Now in this problem again, now what we had changed is that we have changed the supply voltage itself. Remember, everything was operating at plus minus 15 volts, and now they're saying you go to plus minus 10 volts. The question says that. And now what is the change in the frequency of oscillation? Okay, so we have derived as a formula, which was, I believe, R2 by 4RC times R1. Now you can clearly see that it is no way at all dependent on VSAT, right? There's no dependence on VSAT. Okay, so is this a problem? That's just, so you put in the values and you'll see that it come out to be 1.4 kilohertz, which was the question 8 where we solved it. Okay, so that is the option. But what does it mean? Why is it not changing? That's the question that we need to ask ourselves. So let's analyze it a bit. So this was v02, sorry. This is v02, this time v02, and this is your vsat. Okay, now let's draw our second fellow here, which I draw in purple color. Okay, so we know that from this it starts from, let me do it again, just a second, it's a mistake I made. So I know frequency was it was R2 over 4 RC times R1, which will come out to be 1.4 kilohertz. This is R1, right? So it is coming at the same, but why? So we need to see that. So let me draw this. This is with respect to time. So this is my V out 2, which we saw was square waveform, and we saw that the other waveform was triangular, right? And there its peak was, so if you remember, the V01 peak was nothing but the Vm, which we denoted was VTH mod VTH, which was plus Vsat R1 over R2, which I think was coming out to be around 2.65 volts. Okay, so that saturates at around 2.65 volts for Vsat of 15 volts. So but let's not do that. Let's now keep Vsat as the variable, right? That's the independent variable. Okay, so this R1 over R2, so I need to find the ratio of R1 over R2. That will help us. Let's do that. 1.2 over 6.8, that comes out to be around 0.18. This is coming out to be around 0.18 Vsat. Okay, so this is plus Vsat, this is minus Vsat, so it's only around 1/6 of it. That's the maximum. Okay, so it will go from here till here, and then like this. It will keep on oscillating. Okay, and this value is 0.18 Vsat minus 0.18, and this is plus 0.18 Vsat. Now, even if you change Vsat, you change it from 15 to 10, what's going to happen is that this will shrink only in vertical direction, like only in this direction. Okay, why it's not changing? Because the slope, because this period is dependent on the slope, and the slope, if you remember, was given by 1 over RC. Okay, there is a factor of that also, VSAT also, but that gets nullified because this charging is the one that's important on over RC slope. Okay, so what's going to happen is that this is only going to shrink or expand when you change VSAT only in the vertical direction. The horizontal direction, it's independent of it, as if it looks like it's independent of it, which we can also see in numerical terms. It's independent, and qualitatively also you can here see that, because everything will shrink in vertical direction proportionally. Hence your time taken to switch from here to here in this rising side or the falling, it will remain the same. All right, so hence we obtain that the result for this question comes out the same as the original one, which is 1.42 kilohertz. Right, so up until here we have discussed a lot of problems related to Schmitt trigger, and especially which were focusing on the low and high trigger points, the trip points, which were also called. And we saw that in the, especially in the previous sets of problems, we saw how we can integrate two stages. So you can see that just here, if I if I integrated, and if two stages, first is an integrator, second is a Schmitt trigger, we can generate. So here we can generate an output, a square waveform. Here we can generate a triangular waveform, right? And you can see that we can change their frequencies and their slopes and many other things we have controlled just by controlling RC, R1 and R2. Okay, so this is a very powerful tool that Schmitt triggers provide us. It's for positive feedback circuit. Okay, another one of the core things in oscillators is that it has to be like the output, if we want sinusoidal, it should be sinusoidal. Okay, it should not be any other strange waveform when we are opting for sinusoidal. Okay, that is ensured by Barkhausen criteria. The more details you can see in lecture slides of Professor Patil, but here I'm restricting myself to just to the things that are relevant to us. So the problem saying the circuit shown in the figure is an oscillator based on Barkhausen criteria. Gain limiter network is not shown. That's what you refer to the lecture slides for this information. What is the oscillation frequency with R equal to 6.8 and C equal to 47 nanofarad? So this is the circuit that has been given to us. So a quick overview of Barkhausen criteria. So this is your amplifier, your op-amp essentially, and you are feeding an input over here, and there's a frequency sensitive network over here. And so this is the output, and this is a negative, this is a positive feedback you can see from this plus sign, and this is fed into the amplifier. And so the gain for this amplifier turns out to be this is the open loop gain, this is the closed loop gain, turns out to be frequency dependent in domain like this, right? And we can also represent it using this formula, because this is an oscillator, so this is irrelevant. This is a self-sustaining oscillation that it can provide. So and in this problem we are also required to just skip the gain limiter, so we'll not talk about it, just only talk about amplifier and the frequency sensitive network. Now the key thing to note is that Barkhausen criteria says that the denominator has to be 0. So this means that 1 should be equal to A j omega times B j omega. So in the frequency domain, okay, A is the gain of the open loop, right? And B is the gain of your frequency sensitive network. So the product of those has to be equal to 1. So that is essentially the Barkhausen criteria that is for us. All right. Now let's go ahead and solving that. So what I'll do is, that for first part I'll just try to find is the open loop gain. Okay, so that open loop gain will be provided by only this part. All right, so let's try to evaluate that. So this is minus, this is plus, this is V0, this is R2, this is R1, this is grounded, and we will be providing input from here. Remember, only interested in finding A. So step 1 is find open loop gain. Okay, and we know that for this is a configuration that we have talked about many times. Okay, this is in the negative feedback with input at the non-inverting terminal, and we saw that the gain here comes out to be 1 plus R2 over R1 times Vi. This you can refer to the lecture notes or some previous videos. So this is the result we have derived many times. So this is the open loop gain. So essentially the value of A, which is V0 over Vi, comes out to be 1 plus R2 over R1. Okay, now as a step 2, what I'll do, we'll find what is the beta, that is the gain of just the feedback network. Feedback network you can see over here. Okay, so what I'll try to do is let's just try to figure that out. So I'm only interested only in the lower part right now. Okay, so I'll draw this circuit accordingly. Let's ground this. This is V0, this is R, C, R, and then C from here, and this is grounded, this is also grounded. Okay, this node I'm saying is V plus, this node let's call it V1. Okay, so essentially beta, which is nothing but V0 by V plus, I'm interested in finding this value, V0 over V plus. So let's do that. So essentially it's just a nodal analysis problem and nothing else. What I'll try to do is I'll redraw this, okay, in terms of the frequency domain. Okay, so I'm reducing it to this. This is V0, this will remain as R. Okay, this I'll write as 1 over j omega c. This also I'll write as 1 over j omega c. This will be resistance, and then this will be like this. This we noted V1, this was V plus, this is negative, this is positive, and let's just ground this fellow. Okay, so yeah, so when we try to analyze this, so what I'll do is that, so let's first apply KCL over at this node. Okay, so let's do KCL at V1. Let's also name some currents, I1, I2 and I3. No current can flow here because we're assuming it's an Rn is very high. So I1 must be equal to I2 plus I3. I1 must be equal to I2 plus I3. What's the value of I1? I1 can be written as V0 minus V1 over R. Simply I2 can be written as, I2 is the current through here, that is V1 minus 0 over 1 upon j omega c, and I3 can be written as V1 minus 0, this whole branch, okay, divide by, this is R plus 1 upon j omega c, because they are in series, hence I can write. So from this I can obtain V1. It's very straightforward. You can see, just take all the V1 terms to one side. So V1 will be nothing but V0 by R, right? And you take this term here, so it will be 1 by R plus one upon j omega c second. Sorry, it will be 1 upon 1 over j omega c, because that's the thing that is over here, because its coefficient is, just give me a second. Let's just try to solve this in a proper manner. Okay, so let's not hurry. So it will be V1, the coefficient will be, first term would be 1 by R second term would be plus j omega c, because that will come in the numerator, and the third term will come from here. Okay, so that will be j omega c plus 1 upon j omega rc. This whole term will be equal to V0 by R, right? That is how it will look like. And if I send it to the other side, and if we also take R as the LCM, okay, so this will turn out to be V0 divided by 1 plus j omega rc plus j omega rc over 1 plus j omega rc. So that's how no, this is the value of V1, but we also need to find the value of V plus. Okay, so how do we do that? This is just a simple potential divider. Okay, from this I can write that V plus is nothing but equal to R by R plus 1 upon j omega c times V1. This was V1, this was V plus. Okay, so if we do that, so it will be a V1, the expression is this. Okay, so it will be V naught R, and you take j omega c as LCM, it will be like this, times 1 plus j omega RC times 1 plus j omega RC plus j omega RC over 1 plus j omega RC. Okay, so from this I can obtain beta, which is nothing but V naught by V plus. Okay, so if I obtain beta as V naught by V plus, so this everything will goes in the numerator, so this will become 1 plus j omega RC 1 plus j omega RC plus j omega RC over 1 plus j omega RC divided by this fellow, j omega RC. Okay, now if you take this term inside, multiplied 1 plus j omega RC, you will get 1 plus j omega RC whole squared plus j omega RC over j omega RC. Okay, so these are the terms that we are getting. There might be a mistake somewhere. Let me just see. Did I make a mistake somewhere? So this is correct. What about this? In V1 it will be 1 over R, so it will be 1 plus j omega RC plus j omega RC, so there is an R here. Actually no, okay, that gets cancelled, sorry. So 1 plus j omega RC plus j omega RC divided by 1 plus j omega, so that is correct, this part is correct, and V1 is nothing but some fraction of V plus is some fraction of VR, so that's R, and then I put this fellow, so this j omega C comes upstairs, yeah, that's correct. This V1 plus j omega RC, and the rest of the term will remain like this, so yeah, this is correct. All right, so so if we solve it, right, so if we try to, okay, sorry, beta is inverse of this, sorry, beta is inverse, so this is 1 upon beta actually, so this will give me beta equal to j omega RC divided by so I am now opening this, so this will be 1 minus j square is nothing but minus 1, so it will be omega RC whole squared plus 3 j omega RC. Okay, so and we also know that, and so I'm going to use some space, okay, let's do that. We also know that a times beta must be 1, right, which is a real number. A is also a real number, so beta has to be a real number. That can happen only when this term is 0, right, because then j and j will get cancelled, otherwise it will never be 0. So this will imply that 1 minus omega RC whole squared has to be equal to 0, right. This will give me omega equal to, sorry, this is omega square also, so this will give me omega equal to 1 over RC, and if omega is 1 over RC, frequency is 1 over 2 pi RC. Now it's just a simple thing of putting in the numbers, so it will be 2 times pi times, it's the value of R is 6.8 times C, which is 47, so this turns out to be 2000, so that's 1 over 2000, sorry, so in the numerator if I take it, this will turn out to be 500. Okay, so this you put in the numbers, it's coming out to be 500 Hertz, which is option D. Okay, just a quick summary of it. How we did it was that so we know that a beta should be equal to 1, which is from this, then only Barkhausen criteria is satisfied. First we find the open loop gain, because you know this is using that this is a negative feedback non-inverting amplifier which has this gain, so a turns out to be this. All right, and then we finally find out the expression for beta, right, and when we evaluate the expression for beta, so it turns out to be, okay, did I do it wrong again? Yeah, then we apply the potential divider and everything, sorry, this was correct actually earlier, let me just see, yeah, it was correct. Yeah, it was correct earlier, sorry, it was my bad, so this was indeed beta, this was correct, so this was beta. Alright, so beta we evaluated this, and we know a times beta should be equal to 1, which is a real number. This means the imaginary part of this has to be cancelled out. So if we expanded it, it comes out to be something like this: 1 minus omega RC whole squared plus 3j omega RC upon j omega RC. A is a real number, so beta has to be real number. When will beta be a real number? Then the imaginary parts gets cancelled out. That will happen only when this real part is 0, which is C here. Omega equal to 1 by RC. I get the frequency as 1 over 2 pi RC is 500 Hertz. Right. Now the question is, what is the minimum value of R2 by R1 required for this circuit to oscillate? Okay, that's again easy to find. We saw that A beta must be equal to 1. A we saw was 1 plus R2 over R1. Beta is here, 1 minus omega RC whole squared plus 3 j omega RC upon j omega RC. This should be equal to 1. Right. So I think I'm just give me a second. So it's xf equal to beta x naught. Yeah, so beta is xf upon x naught. Yeah, so I was correct in the second part. So this is indeed 1 over beta. Okay, this is 1 over beta. So this means minus 1. So this turns out to be 0. So we get 1 plus R2 over R1 times j omega RC over 3 j omega RC. This should be equal to 1. This term gets cancelled. So 1 plus R2 over R1. See, now it's coming out to 1 by 3, which must come, right? This turns out to be 3. So we get R2 over R1 equal to 2. Okay. So R2 over R1 must be equal to 2, which happens in this question. Sorry about that confusion over there about the expression for x, for beta, sorry. So beta is V naught upon, V plus upon V naught. Okay, so that's what we did here. And yeah, so we solved it, found the frequency, found the value of the ratio of R1 and R2, which turns out to be 2. And that is all for today from my side. We have finished just on time. And if you have any comments or questions, please feel free to ask. Sorry about the hip hop at last. Okay, if nothing, then let's close this session. We'll see again. I'll see you again on the next week. From next week onwards, we're starting digital electronics, the next 3 sessions. So their concepts are not so much involved, in the sense that it's much more intuitive, and the problems are numerically much less lengthier. It's more of an involved type of thing. So I'll see you next week then. Thank you for your time.